Hi everyone, my name is Jose Correa with Team 13 and we're excited to present our senior design project, a custom built power distribution module, or PDM for short. This is going straight to FIU's Formula SAE race car club, and I just want you guys to think about the PDM as the electrical backbone of the vehicle. It distributes power and protects sensitive components from overcurrent and short circuits. Traditionally, this has been done using really bulky relays and inline fuses. These parts, they're often unreliable and hard to diagnose when something just goes wrong. Our solution is a modern solid-state PDM that replaces mechanical switches with semiconductor devices and e-fuses. It features built-in diagnostics, data logging, and CAN integration, meaning the car now detects, reports, and even isolates electrical faults on its own. Troubleshooting, which used to be done manually, checking fuses with a multimeter, now happens in real time. We're also developing remote monitoring capabilities and exploring wireless options like Bluetooth, Wi-Fi, cellular modem, radio frequencies to find the best fit for the team. Marketability. Just imagine, in racing, a single electrical issue can ruin your day. It destroys the whole event, and even if it's just a blown $2 fuse, that's not just frustrating, it's avoidable. FSAE teams often struggle with tangled wiring, no fault detection, and expensive commercial PDMs that cost well over $1,000 and require advanced setups. Our PDM changes that. It simplifies the wiring, it reduces connection points, and adds intelligent features like smart switching. And smart switching is basically, imagine the fan suddenly draws way too much current. The PDM will shut it off and log the issue automatically, protecting the rest of the system from damage as well. And instead of relying on relays or switches, it uses logic-based control. You just define the rule and the PDM handles the rest. We've also developed a Bluetooth-enabled app using React to provide real-time feedback, and you can see faults, logs, and current draws live, all on your phone or laptop. At an estimated cost of like $200 to $300, our design brings the reliability and functionality of a high-end PDM for students, made by students. So the problem is clear. Student-built race cars need better electrical reliability. The old ways, tangled wiring, mechanical fuses, and guesswork just don't cut it anymore. So our objective is to build a reliable, affordable, and smart PDM designed for FSAE use. It had to provide diagnostics, protect against cascading failures, and make troubleshooting as fast and simple as possible. We're proud to say our design meets all of our goals and gives the team the tools they need to focus on performance, not power problems. Thank you.
The intended use case of the power distribution module is for the Florida International University's FSAE team. FSAE stands for Formula Society of Automotive Engineers. In this competition, the team builds a Formula-style vehicle and goes to compete at Michigan International Speedway every year against 120 universities worldwide. From there, they take their design plans and the vehicle to the competition and present it to industry giant judges. Judges that come from Ford, Toyota, Tesla, Stellantis, SpaceX, Blue Origins, etc. From there, the team will take the car on the track and do time trials of acceleration, skid pad, autocross, and most importantly, endurance, which is a 9-kilometer race. The team will benefit from a PDM for the use case of power distribution and reliability and data. The two main users at this competition and for this PDM will be the electrical engineer and the data acquisition engineer. The electrical engineer will use the PDM in order to change fuse currents, right? Step up the fuse current limitation or drop it, instead of going inside the car, which can be quite cumbersome, as to get to the fuse box currently you have to take up a few components to take it off. Then from getting the fuse box, the electrical engineer would have to take out fuses, check them visually, put them back in, or swap them. For relays, take it off, shake it to see if there's any loose components, and put them back on or swap it. The electrical engineer doesn't have to do that again. Instead, he can plug into the computer, into the car, and basically through his computer, through an interface, can change everything. He can turn fuses back on, change the current limitation values on those fuses, turn on switches automatically, and test them out. The electrical engineer will have safety nets such as overcurrent, overvoltage, undercurrent, short circuit protections, and polarity protections to ensure that the PDM never breaks, unlike fuses and relays. The data acquisition engineer will benefit from the PDM because now they would have data that they can use to validate components of the car during the design process of the car. The data acquisition engineer, after a race, can take the logs, see in a time track and a time lapse what current is happening for each power output, voltage and power, and from that he can validate different components such as battery selection or wire harness. Right? The data acquisition engineer can take the values and see, hey, maybe we need to step up the battery capacity from 8 amp hours to 12 amp hours as all our power outputs are draining the battery. For the wire harness, he can look at the fuel pump wires and say, hey, I can see through the current we're doing 5 amps. A 22 gauge cannot handle this, so we're going to step it down to 20 gauge. And this is the added benefit for both users. I already went in through the benefits for each user through here, but I'll add more benefits to it. It's programmable. Unlike traditional fuse boxes, like I said, manual labor. Everything is configurable through a nice interface and simple enough to collect data and change configurations. Also, the data collection is a neat benefit as it can distribute information through a controller area network. Right? The car will have a centralized logger, and that will collect data for the data acquisition engineer to compare with the rest of the data. Another thing is the reduced long-term cost of fuses and relays. Every time a fuse breaks and a relay breaks, that's an added cost. And then in the iteration stage of adding new power components, you can see that selecting new fuses might break it, and you'd have to buy many fuses and relays. And that can be a long-term cost that a PDM can avoid. Also, packaging. As you can see over here, this is the current layout of the car, with the fuse box down here, and this is a power distribution module with no electronic components except for a battery fuse. Now, the overall goal is to make a nice packaging where we basically combine these two components and everything is electrical. And we can just put it on, as you can see, this metal sheet, which is the firewall, just put it on there, and that's our new power distribution, which should never be touched and can be plugged in electronically. Another thing we need to take into consideration is intellectual property. At least for the components, electrical components, intellectual property comes with the purchases. If you purchase, for example, an STM32 controller, it already comes with the ARM architecture licenses. ARM architecture licenses, unlike the RISC-V cores, are licensed and patented by ARM. But with the purchase of it, it comes with it. We will try to find open source designs if we need to integrate, or base designs that are used for power distribution means. We will try to navigate our way to avoid patents when it comes to the hardware design of components, and also for the software. When it comes to designing the software, from firmware to high-level interfaces, everything will be done with OSS licenses, such as the MIT license, which allow free usage and also modification without ramifications. Also, open source software for designing, such as KeyCAD, which is an open source license, which you can use to design your PCB. NeoVim and VS Code are text editors that you can use for programming. And then we have things like Postgres for database. It's a MySQL-based database that is open source, and it can be used without any ramifications of licenses, patents, etc.
Hello, my name is Daniel Picao, and I'd like to start by talking about ethical considerations. I'll talk about the ethical dilemma, our solution to the dilemma, and our concept of the good life. So to start, our PDM is an active cutoff, has cutoff capabilities. How could that be an issue? Well, in the motorsport industry, we tend to see that maybe not the engineers or even the driver, sometimes even the track and the environment in which the car is in can cause some issues with sensors going bad, things going left, things working the way they're not supposed to, and that kind of poses an ethical challenge for us. So how do we solve that? How do we solve if something goes wrong? Our solution to this is called multi-tier validation protocol, which pretty much just means that we have some subsystems in the vehicle that if something goes wrong, if something's not working the way it's supposed to, our PDM goes into what we call limp mode. When in the limp mode, it immediately sends alerts to us engineers, or if we want, the driver as well, and it tells us when this happened, what exactly stopped working, and it just gives partial control as well to the driver, because we don't want the entire car to shut off as well. Our concept of the good life, I mean, our team views, engineering as like where safety and autonomy and, a trust in the system is kind of just coexisting all together. Technology in our case is very important because of the nature of motorsports. We don't want it to completely eliminate the human decision making, right? So we want to make sure that whatever it is that we create, we don't replace human judgment, which is one of the very important things that we want to keep in mind while creating this PDM. Our concept selection. So what we're going to do, we finalize this kind of a microcontroller based power distribution module for solid state switching, which that brings real-time data evaluation, current voltage. If you want to change your pin to a certain kind of current voltage, we can do that as well here. Our communication is going to be using Canvas, right? So this opens doors to telecommunications, whether that be Bluetooth or Wi-Fi. They could be Wi-Fi as well. Discarded concepts. So what we want to discard was, as you can see, the photos that Carlos spoke about. It's pretty much what we call a rat's nest of wires, right? So we want to make sure that whatever it is that we create, we were able to kind of have something a lot more organized. And unlike our PDM, it just lacked diagnostic features. It just sucked at not only just the weight too, but the wire management and just kind of fixing and repairing. It was just a hassle. Again, the fuse relay the system that we currently have on the car just had no type of communication. We couldn't get any data from it. We didn't know how performance would be, what we could do to increase performance. There was no communication. And again, it was non-modular. It was difficult to debug, to repair it, and just the scalability of it, which is really important to us. It just sucked. We weren't able to scale on that. It was just a system, and that's it. There was nothing we could really implement in it. So to conclude, our PDM is the most significant upgrade that we've had pretty much ever in the FSAE. I mean, electrical wise. We by combining all these switchings and real-time monitoring and things like Canvas, not only does it give us an availability to improve performance, but most importantly, it just improves safety, right? And we have this transparency of data in which we can go back and log these things and try to pinpoint where things are going wrong. It's very, very helpful for us. It's important to know here that the PDM is not a replacement of the fuse and relays. It's much more than that. It's a diagnostic. It's a protection system, not only for the vehicle and the sensors that we have in the car, but most importantly to the driver as well. And it's modular. It's a microcontroller base. You can, like we were just talking about, we can change the pins on it. Certain voltage, certain current, and of course opening the doors again to telemetry, which would be ideal for our system as well. In summary, our design reflects our commitment to what we're calling engineering excellence, which just falls under smart integration of our embedded system, reliability, and of course we don't have it here, but just user safety, driver safety, engineering safety. Safety is definitely one of our top things that we're trying to hit in this project. As well as very, very important that we want to lay out groundwork, and not just for a very competitive car and a resilient car, but something that we can leave off for future engineers, so they can build on top of that and create something greater, something more customizable. And yeah, thank you.